Let's begin our journey into the world of computer vision. Computer vision is all about teaching computers to see and understand the visual world, much like how humans do. Consider it as equipping computers with the ability to interpret images and videos. We will explore the amazing possibilities of image recognition, processing, and gaining insights from visual data. To understand computer vision, we first need to grasp the basics of digital images. Think of a digital image as a two-dimensional grid of pixels. Each pixel holds color information. The example here illustrates a simple grayscale image matrix. We import the NumPy library, a powerful tool for numerical operations in Python, and then create a matrix representing a grayscale image. Each number in the matrix corresponds to the intensity of a pixel. Values range from 0, which represents black, to 255, which represents white, with various shades of gray in between. Before feeding images to computer vision models, it's crucial to pre-process them to enhance their quality and make them easier to analyze. Several techniques are commonly used. Noise reduction involves removing unwanted variations in image intensity to improve clarity. Contrast enhancement adjusts pixel intensities to improve image visibility and details. Color space conversion transforms images between different color representations such as RGB, which represents red, green, and blue, HSV, which represents hue, saturation, and value or grayscale. Image resizing scales images to desired dimensions while preserving important features. Feature detection and extraction are essential steps in computer vision for identifying and highlighting important parts of an image. Corner detection pinpoints distinct corner points that remain stable, even when the image is transformed. Scale invariant feature transform, also known as SIFT, detects and describes local features in images, enabling the system to recognize objects regardless of their size or orientation. The code snippet shows an example using the OpenCV library to initialize a SIFT detector, find key points, compute descriptors, and draw the key points on the image. Edge detection is a fundamental technique in computer vision used to identify the boundaries of objects within an image. The Sobel operator computes image gradients in the x and y directions to detect edges. The canny edge detection is a multi-stage algorithm that effectively detects edges while suppressing noise. It involves noise reduction using a Gaussian filter, gradient calculation using Sobel operator, non-maximum suppression, and double thresholding with edge tracking. Pattern recognition is a core aspect of computer vision, enabling machines to identify recurring patterns within images. The process typically involves several key steps. First is feature extraction, where key characteristics that distinguish different patterns are identified in the image data. Training then involves learning from labeled examples to build a model capable of recognizing similar patterns. Next, classification categorizes new inputs based on the learned patterns and features. Lastly, validation evaluates the recognition accuracy and refines the model as needed. Object detection is a critical area in computer vision that involves identifying and locating specific objects within an image or video. Several algorithms are commonly used for object detection. YOLO, which stands for You Only Look Once, is a real-time object detection system that processes images in a single pass through a neural network. The RCNN family, which means region-based convolutional neural networks, propose regions and classify objects within those regions. SSD, which is single-shot detector, balances speed and accuracy by evaluating multiple scales in a single network forward pass. Convolutional neural networks, often called CNNs, are a class of deep neural networks widely used in computer vision for tasks such as image classification and object detection. The structure of a CNN typically includes an input layer, convolutional layers for feature extraction using filters, pooling layers for dimensionality reduction, and dense layers for classification based on the extracted features. In this code example, we define a simple CNN model using TensorFlow and Keras. The model consists of convolutional layers with ReLU activation functions, max pooling layers, and a dense layer with softmax activation for classification. Computer vision has a wide array of applications across various industries, impacting our daily lives in numerous ways. Face recognition technology is used in biometric authentication systems, security and surveillance, and social media tagging. Medical imaging utilizes computer vision for disease detection, tumor identification, and X-ray analysis. Autonomous vehicles rely on computer vision for object detection, lane detection, and distance estimation. Industrial inspection employs computer vision for quality control, defect detection, and assembly verification. The field of computer vision is constantly evolving, with several exciting trends shaping its future. 3D vision and depth perception are advancing to provide a more comprehensive understanding of real-time environments. Multimodal learning is integrating vision with other sensory inputs for more comprehensive scene understanding. Edge computing is enabling efficient processing of visual data on edge devices with optimized neural networks. Zero-shot learning is allowing the recognition of new objects without prior training examples through advanced knowledge transfer. Over the next few years, expect to see real-time 3D scene understanding, neural architecture evolution, quantum computer vision algorithms, and human-level scene understanding. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.